So let's get things started. My name is Sukmanu Lal, and I'm at the Water Institute at ASU, and it's our pleasure to bring you today's talk by Kornhuber, who's at the International Institute for Applied Systems Analysis in Vienna. His background is in climate physics from the University of Potsdam and the Potsdam Institute of Climate Impact Research. And he's one of the more exciting younger researchers in climate. And much of his work relates to trying to understand the dynamics of extremes, uh, how we can do attribution, how we can understand what is why they are changing, and then also connecting them to the impacts of those extremes. And this is exactly the basis of his talk today. And he's covered many aspects of climate extremes, actually. So I'm excited to see what he's going to talk about. He's also been at the Columbia Climate School and specifically working with the Lamont Doherty Earth Observatory, both teaching a class at Columbia and working with researchers at Lamont. So it's a pleasure to have a colleague of mine from Columbia come and give a talk to us today. You will see that it's quite exciting. His talk will be about 45 minutes, and given the format and given that it's 8 p.m. there in Vienna, we were thinking that it would be nice if you guys can record your questions or hold them until the end of his talk, and then there will be an opportunity to ask the questions. You can raise your hand and we will call in turn. You may also want to put your questions in chat because then we can aggregate those questions and then ask him once instead of, people are repeatedly asking very similar questions. Also, he has shared 4 papers with us of his recent work, and those are getting posted in chat as well. So with that, let me welcome Kai, and let's get the talk going. Thank you very much, Kai, for joining us today, and to everyone for joining the call.
Thanks so much, Manu, and also, Corey, for organizing this and for inviting me to speak today here at the Climate and Water Future Seminar. Really excited to talk about these recent results that we produced, so which are part of these sets of papers that we shared earlier, and a couple are also not published yet. So these will be the subject of my talk now. So I will talk about physical drivers and statistical properties of high impact climate extremes. You will see that this talk is mostly about heat extremes because that's one of the most impactful natural hazard, and it's also most directly connected to global warming, as you probably are aware of. So let's go right in. As a motivation, heat extremes are really among the most deadliest disasters globally, right next to earthquakes and major storm events. The European and the Russian heat waves produced several 10,000s of casualties, and more recent heat waves such as the 2022 heat wave in Europe is right next to them. So really a very impactful climate impact driver. They are so severe that you can actually see the impacts in these annual excess death charts that were produced during the COVID-19 pandemic. Here, such a graphic over France, and you can see this intense spike here as the signal that was produced by the 2003 heat wave over France. Similarly, here a figure from the Financial Times at the beginning of the COVID pandemic. You see that this is from 2020 in April, where this whole thing just started. In gray, you can see the outline of the casualties from the summer 2010 heat wave there. But heat waves are not only deadly, they also cause a number of other unexpected impacts, such as impacts on infrastructure, energy, and aviation, for instance. So this is an example from last year where Third Avenue Bridge was stuck in an open position and um, disrupted traffic for several hours during rush hour because the steel construction expanded too much in the summer heat. Another impact from heat are, of course, wildfires and the toxic pollution that they bring. This is from 2023 when the smoke from Canadian wildfires were brought to New York, really bringing daily life to a halt and triggering these emergency measures. A lot of outdoor activities, events were canceled, air traffic was halted, and so on. This really happens, every now and then, and increasingly often. This is another example from last year when the smoke from these wildfires actually were carried by the large-scale circulation to Europe with a clearly detectable signal here in the lower corner over the UK. So many impacts from heat extremes, some of which are not necessarily intuitive. And as you are probably aware of, we are seeing more record-breaking temperatures over almost all months of the year. So this year, January was just another record after several records in 2023 and 2024. And I'll talk a bit about the 2023 summer, which still scores as one of the hottest periods this Earth has experienced in the recent centuries. So this is a paper that really provides a nice overview of how extreme 2023 really was. This was led by Sarah Perkins Kirkpatrick with several co-authors. And this paper, we find that and not only was the year overall second hottest on record, but 23% of all land regions experienced record-breaking temperatures, which you can see here as a number of heatwave days, that global figure, which is really an extraordinary amount if you think about it. So almost a quarter of all land surface experienced hottest temperatures over the observational time period. And yeah, this is just basically the latest data point in a series of events. And what I really like about this figure here from a paper by Alex Robertson and colleagues is that it nicely illustrates that the Earth's surface is now experiencing heat extremes at a magnitude it has not witnessed before, at least over the periods in which human civilization played a major role. We see that there's a stability in these types of 1 sigma events up until the 80s, until they start to increase. And new types of extremes start to emerging now with each decade almost. So now starting in 2000s, we are seeing these types of 3 sigma events, and just recently the emergence of these 4 sigma events. And if you have paid attention to the media and the coverage of extreme weather events. And you probably didn't miss this event, which was a 5 sigma event, really unprecedented, the record-shattering 2021 Pacific Northwest heat wave that was so extreme that it kind of messed with the statistics of regional temperature extremes. So if you include this event in your generalized extreme value approximation, then the whole distribution and the return times really do shift. And yeah, the World Weather Attribution Project back then mentioned that yeah, this event was basically impossible without anthropogenic climate change because of that reason. Um, Another event recently over Europe where 40 degrees were measured over the UK. Very particularly event also because wildfires were for the first time seen around London. Truly apocalyptic images from that particular event. So all in all, this is not too surprising, of course. We know that with rising greenhouse gas concentrations in the atmosphere, we experience warmer temperatures, which lead to a shift also in daily temperatures and daily extreme temperatures. And on top of that, there are, of course, other effects that are a bit more complex, which affect the shape of that distribution. So we see basically more heavy tails, so an increase in the most extreme temperatures because of changes in the kurtosis, so an increase in variance and skewness. So the temperature curves in some regions become more and more asymmetric because on top of these direct thermodynamic effects from global warming, which act on temperatures globally, we do have more regional effects from land atmosphere feedbacks, atmosphere dynamical changes, and other aspects linked, for instance, to vegetational changes or seasonal effects. And this overall might lead to an acceleration of heat extremes. So more record-breaking, more unprecedented extremes that might also increase at an accelerated rate. On top of that, we do expect more complicated, more complex extremes. So on top of record-breaking extremes, there will also be concurrent extremes, extremes in seasons that have not witnessed certain types of phenomena in the past, more extremes that happen back to back, and also longer lasting extremes. And of course, these all might amplify impacts in ways that are really difficult to assess. Because we don't have that much time, I will really focus on these two aspects today, and we'll discuss what we can say about these phenomena based on observational time series and model data, and will also touch a bit upon physical mechanisms that are associated with these two types of extreme weather characteristics, so record-breaking extremes and concurrent extremes. And I will follow this outline, which is based on a few papers that me and my group published over the past years, starting with a paper that investigated the global emergence of regional heatwave hotspots, and a paper that looks into atmosphere dynamical drivers of these hotspots. A paper that is currently under revision that looks into land-atmosphere interactions and nonlinear amplification of heat waves, and then a few papers that look into drivers and impacts of concurrent heat waves. So how do we actually know if these tails are becoming more and more heavy? For this, we really need to look into local temperature distributions and assess to what degree specific parts of the distribution change year to year. And this is what we did here in this study, in which we looked to what degree this part of the distribution is changing by subtracting the 87.5th percentile from the 99th percentile of daily maximum 2-meter temperatures for each grid point and for each year. And we then did a linear regression of these annual values and reanalysis data and managed to identify global hotspots for these types of tail widening trends. So each of these regions that appear red here experience a significant trend in tail widening, which means that the more extreme temperature days rise faster than the more moderate ones. Basically measured for increasing skewness of the distribution. And we identify a couple of areas, in particular Western Europe is here identified as a heat wave hotspot. And this follows a series of papers that have looked at this type of phenomena, basically investigating the most extreme temperatures versus more moderate ones with various methods. So I just wanted to point out a few of these studies here, which find different patterns because they look into different parts of the distribution. So this paper here by Chris Huntingford and colleagues, they look into the median temperatures and the ratio. And this paper here looks into the hottest temperatures versus the average. But several patterns do emerge. So we do have a couple of regional heat wave hotspots visible over the observational time period in which the hottest temperatures really increase faster than the more moderate ones. And one question that was really in the center of this whole analysis was also to assess to what degree state-of-the-art climate models, so these climate models that are currently being used for future risk assessments and also for assessing possible impacts under various emission scenarios are dealing with these types of events. And we looked into a series of models and then checked to what degree these trends fall into the observed trends. And we find that the spread of the model trends in these particular heatwave regions does often not include the observed signal. This can be seen here in the map, where dark red regions highlight those areas where the observed signal is outside of the spread of possible modeled trends. And this can also be shown here in these box plots that we generated over these particular areas, where this becomes even more evident that observations in some of these areas are really outside of the model spread, or at least at the far end of what models think is possible. This can also be assessed, of course, in a more globally aggregated way. So this is now a density plot that shows all grid points and all trends over all grid points in a logarithmic scale to highlight these tails of these trends a bit better. And in red, we show trends from era 5. You can see that for these more intense trend, for these stronger trends, era 5 shows a significantly stronger amount of grid points globally. This can be also shown in this way where we look at the probability ratio. So positive trends above 0.5 degree per decade are 4.1-fold less likely in models. So we do see an underestimation of these types of accelerated heat wave trends in models. And of course, next question would be, why is that? What is it that the models do not properly reproduce? That is a very important question to ask, of course. I mean, because of curiosity, of course, but B, we really need these models to make good decisions about the future, about climate adaptation and so on. So if we're really off by a lot because we do not get certain processes right, that will lead to wrong decisions, and in the worst case, lead to amplified impacts and maladaptation. So this really nice figure is from a review paper from David Barrio Pedro from 2023, which shows different heat wave processes arranged by spatial and temporal scales. And in principle, all of these aspects could become relevant on the local scale to mess with the modeled signal. But specific drivers have been identified in the past that are particularly difficult for models to capture. This is because they're very complex and they act on time scales and spatial scales that are really hard to resolve in models, and also interact with a lot of other components of climate models, which is true, for instance, for moisture, soil moisture, but also aerosols, and of course clouds. So in the next couple of slides, I will discuss a couple of these papers and show evidence for why specific trends might not be properly reproduced due to these due to specific biases in these processes that I have listed here. So let's start with the atmospheric circulation. The large-scale circulation, so the jet stream and the storm tracks, so these fast-flowing winds in upper altitudes of 10 kilometers and so on, 300 millibars, they really determine our weather patterns in the mid-latitudes. That includes North America, Europe, Eurasia, and any change in this large-scale circulation will have a direct effect on extreme weather conditions, or at least weather conditions in general. There have been two trends observed that are relevant for summer. The first one is a summertime circumglobal teleconnection that is evident or visible as trends in specific regions highlighted here and geopotential height anomalies. So we see higher pressure patterns here emerging over the past decades, which directly link to warmer temperatures in over the surface. And the second trend is the weakening of storm tracks. So the northern hemisphere summer circulation is getting weaker and slower, which might affect weather persistence. So weather patterns, high and low weather patterns might remain more stationary over specific regions, which can drive more extreme weather situations. So if you think about a specific weather pattern, a high pressure system over a region, if it leads to fair weather on one day, if it remains for like a week or so, that weather can quickly turn into a heat wave because of specific land atmosphere interactions and response of the vegetation. And linked to that weakening of the storm tracks are specific atmosphere dynamical patterns that we call double jets. So imagine taking an average of the zonal wind over Eurasia. So you can see the map here. And these are the winds that flow from west to the east. So these are called zonal winds. If you take an average over that box, basically, you can build these types of profiles. And using self-organizing map methodology, we cluster these types of profiles into three bigger patterns. And one of them is a double jet. And you can see here from that composite of all these double jet events that this double jet pattern is characterized by strong winds in the northern latitudes and in the subtropics, but very weak winds in the mid latitudes, and that relates also to weaker storm tracks. And we also find that this type of pattern shows a significant trend in persistence. So the duration of these types of double jet patterns have been increasing over the past decades. And Europe as a hotspot is directly affected by this. This becomes evident if you look at where these wind patterns really act on weather patterns. You can imagine that the lack of wind over summer, so the lack of new weather patterns that bring moisture and wind during summer can really affect heat wave characteristics. And that is something we can also see from a simple regression when looking at the effect of these double jet patterns on temperature extremes. We find that they are significantly correlated. So these trends in double jets have been contributing to the trends in European heat waves over the past decades. And this is a finding that has since then been validated and confirmed by other papers that have looked at it. So with different methods. So some of them have looked at local weather patterns, others have looked at types of analogs, but they all come to the same conclusion that changes over Europe in terms of the atmosphere dynamics have really contributed to these nonlinear increases of heat waves. Now, can climate models reproduce these types of patterns, and could this possibly be one source of model bias with regard to these heat wave trends? For this, you have to repeat this analysis in climate models. So we looked at CMIP6, which is this big coordinated effort of global modeling centers that is providing freely available climate data output over the historical time periods. And we repeated this analysis, basically finding that most models are able to reproduce these types of double jet patterns, which is reassuring. But interestingly, these patterns do not lead to the same type of temperature anomalies as compared to the signal we get from error 5 reanalysis data. So that dark blue spot here shows the anomalies when we subtract error 5 from the CMIP6 signal, suggesting that the anomalies are lower by multiple factors. So apparently, while the circulation patterns do exist also in CMIP6, the surface temperature response to these patterns really is off, which could be one of the reasons for why Europe is showing up also in this map of underestimated heat wave trends in this figure here. As you can see, it's dark red and models are really far from the observed signal. So this was an atmosphere dynamical reason for why we are seeing these biases over Europe in particular. I want to talk a bit about another aspect which involves the atmosphere dynamics and the land soil surface, in particular soil moisture. It is kind of a canonical finding that or knowledge that the combination of high pressure systems and dry soils are the main ingredients for very extreme heat waves. And this was shown yet again during that 2021 Pacific Northwest heat wave, which really broke all records by extremely large margins. And you can see the temperature anomalies, pressure, atmospheric pressure patterns, and soil moisture anomalies in these three plots here. Again, 12 degrees above the climatology during that particular time period in summer. And it happened at the same time as a very high pressure system being located here and soil moisture anomalies. And what was particularly interesting during that event, which we published on in Nature Climate Change, is that there was a specific divergence of a more or less linear relationship that can usually be observed during these temperature, geopotential height, and soil moisture dependent structures, which are more or less linear. But during that particular heat wave, and you can see the measurements, like the daily temperature values during that heat wave in red diamonds here, it seemed as if that dependent structure was changed to some degree, where the relationship between temperature and soil moisture, for instance, became more intense. So you can see all other values here and the measurements during that heat wave over here. And in that paper, we find that these types of nonlinear interactions really amplified the heat wave magnitude by a percentage of 40. But of course, that was only one event, and we were also limited by the amount of data points and events over the past period over in that particular region. So to follow up on that study and to really assess to what degree these types of nonlinear interactions play a role in amplifying the most extreme heat waves, we set up this hypothesis that you can see here on the right, that we can basically estimate temperatures by direct contributions from atmosphere dynamics and soil moisture deficiencies, and an interaction term between those two, which we assume to become particularly important after a specific temperature threshold is breached. So basically a change in the dependent structure linked to a critical temperature. So with this hypothesis in mind, we used explainable AI framework, which has become increasingly popular. So this is an approach that combines machine learning with SHAP explainer approaches, which allow to retract or reproduce the exact contributions of each of the explainable variables plus the interactive terms among them. It's an approach that was known for a while, and recently in this paper was applied to kidney failure research. There's another paper by Xijie Zhang who analyzed compounding factors of river floods with that approach. And in this study that we have recently submitted, we look at heat waves and these interacting factors. So first of all, we try to see how our model is doing. So this is the European heat wave of 2022. And in this figure, you can see the observed values and the modeled values. And the different components. And this particular event, the model is performing extremely well. I have to admit that this is also a very nice example. There are a couple of other heat waves where it's a bit off, but overall it does perform very, very good. In particular in the mid-latitudes, where we consider atmosphere dynamics very important for heat extremes, atmosphere dynamical variability. So this case, the interacting component contributed 13% of the overall heat wave magnitude to make that event really record-breaking. And that can also be done, of course, globally. So this figure shows this interaction factor for the top 10 heat wave events for each grid point. And again, it shows that this is particularly relevant in the mid-latitude. So these dashed lines here show 20s to 60 degrees in the northern and southern hemisphere. But here, the interaction of these two components really contributes up to 40% or more to the overall magnitude of that heat wave. And again, if we repeat this type of analysis in climate models, we find that over many of these areas that we have identified before as heat wave hotspots, this type of interaction and in particular the nonlinearity is not well reproduced by climate models. So there's something off in the internal dynamics during the emergence and decay of heat waves, apparently. So these two factors, two possible reasons for why climate models do struggle with heat extremes. I will talk a bit about concurrence, and yeah, we do have a bit of time left in this talk. Um, so again, recently we have seen an increase in concurrent heat waves globally. And 2023 was another record-breaking year where the summer experienced many heat extremes that happened at the same time. Another example, 2022, where there was a heat wave in Europe, but also in the central US. And in this particular event and in many others, there was a specific pattern visible in the large-scale circulation. So this is the jet stream, the wind speed in these upper altitudes at 250 hectopascal. You can see how high pressure and low pressure systems basically locate themselves within the ridges and troughs of that meandering jet. And as expected, high pressure systems do very well link to warmer temperatures at the surface, while these low pressure systems are associated with cold. So the strongly meandering jet that was here present during that particular day directly related to these concurrent heat waves that we observed across the entire mid-latitudes. And this is something that can be observed fairly often. So in particular, heat waves that are record-breaking in particular regions because of persistent high pressure systems are linked to these yeah, strongly meandering large scale or like very much extended jet stream patterns in the northern hemisphere. And these are just three examples on top of the one that I just showed. So the diamonds show these record-breaking temperatures, and they do occur at those locations where yeah, the jet stream shows these strong meanders. And this alternating pattern of red and blue here shows basically these north and southward directed winds that you can then combine into this yeah, meandering pattern. So you can somewhat see this in these examples already, but if you look at very specific wave patterns, it becomes even more clear that there are some recurrent patterns in the jet that we do see related to specific regions as well. So in this study, we identified a wave 7 pattern that is called wave 7 because it has 7 ridges and troughs organized around the mid-latitudes. And this pattern, when its amplitude is high, is really located over the same location again and again. And that's not necessarily a given thing. From these types of synoptic scale wave patterns, you would actually expect them to be more or less randomly distributed and also transient, which means that they are not stationary, but they're just like moving from west to east. But this particular pattern shows a very clear relationship between amplitude and phase position. So that means that when there's a high amplitude, the pattern is very intense, the likelihood that we see it over a specific region also increases. And that leads to the fact that if you do a composite of all identified events, we do have a very clear pattern emerging with significant temperature and wind anomalies across the mid-latitudes. And that pattern is leading to more concurrent extremes. So with this study, we looked at the likelihood that specific regions experience extreme temperatures of a particular severity. And using this coincidence analysis approach, we do find that the most intense temperature anomalies are also significantly related with the occurrence of that particular pattern. So if we do see strong temperature extremes here in these regions that we highlight here, there's an increased likelihood that that wave pattern is also present. Why is that relevant for impacts? Well, we do live in a very connected world, and a couple of systems, like the food systems, do have certain choke points that, if they are all affected at the same time, can lead to very severe consequences to people who rely on imports in particular. So this is from another study that we published recently, where this exact pattern that leads to these concurrent extremes is overlaid over mid-latitude major fruit production areas, and a lot of them are in the mid-latitudes. For some grain types, the amount of yields is located by a ratio of up to 60 to 70% in these moderate climate zones in the mid-latitudes, where this pattern is relevant. And we assessed to what degree this pattern actually is affecting crop yields, and it turns out that there is a significant signal. And when we do have these jet patterns in the large-scale circulation present, we also observe an increase or a decrease in yields or decrease in productivity in these particular areas. Interestingly, this effect is not well captured in models, and this is not because of issues with crop modeling. Crop models actually do perform fairly well when we drive them with observations alone, but it is to a large degree linked to the fact that climate models do not show the same type of temperature anomaly when that particular pattern is present. So these are two anomaly patterns, one from ERA 5 and one from a few CMIP6 models. While the atmosphere dynamical pattern is well reproduced, so we can see that the ridges and troughs are really located over the same area, the anomalies are underestimated by almost an order of magnitude, which is when it comes to impacts, of course. So overall, maybe also as a last statement on concurrent heat extremes, this from another paper that was led by Cassandra Rogers. There is a clear increase in concurrent heat extremes, but these are primarily driven by thermodynamic effects. So while these wave patterns are really important for specific impacts, and these impacts will become more severe because the signals, the associated extremes are becoming more severe, the main driver really is the warming itself and not necessarily a higher frequency of these particular patterns. At least this is not yet visible in the observational time or the observational records. So yeah, I provided you with some insights into heat wave statistics, and that some regions are experiencing more extreme heat waves than what the mean would suggest. And that climate models are really struggling because of several dynamical, atmosphere dynamical, and also interactive biases. And maybe to wrap up this talk, I think it's important to note that the heat waves, where they're extremely complex and there are a lot of physical process understanding is still lacking, there's still like the type of extreme or the climate impact driver that we understand best or are capable to model best. And that is maybe expressed here in this nice figure from Ted Shepard that he published in 2014. So change in surface temperature, there's so much more confidence in this compared to changes in precipitation. And that, of course, also is true for extreme precipitation values. So there's even more work to do when it comes to future flood risks, future risk from extreme rainfall, and of course also tropical cyclones, which are also extremely challenging to accurately model. And yeah, maybe as an outlook, I am working with people from the financial sector and people who really use these climate model outputs for their decisions. And there's definitely an increased need and demand for accurate, reliable climate risk estimates for these extreme weather event types and also compound events on a very regional scale. And I believe it's essentially our job as scientists to make the models better, to provide the tools that society needs basically to mitigate the worst risks, but also to raise awareness of the limitations of the climate models, and to make clear that certain things that would be nice to have are at the moment not really available, and that they might require additional very specific modeling efforts on regional scales, including regional experts, to make informed decisions that also help to avoid worst impacts under future emissions. And I know that several climate services, they use basically the CMIP6 outputs and downscale them, and other people basically buy their products and use this information for their purposes, which I believe is very risky. So again, our job as scientists, I believe, is to really raise awareness and to provide transparency into the reliability of these products, and ideally improve them over time. So I know that was a lot of information. I hope a few things will stick with you, and I know that the papers were posted in the chat, so maybe they help to provide further context. In any case, we do have 20 minutes to discuss, so I hope there are a few questions that we can use to start a bit of a discussion. These are my contact data. Please reach out in case you want to learn more about what we do at IIASA. Also a co-chair of this Future Earth network. There's going to be a call soon for steering committee members. So in case you want to get active there, also reach out. And yeah, now look forward to the discussion and also hope to see you all in person at some point. But for
Thanks
now,
very much, Kai. This was very
yeah.
nicely done. Appreciate your taking the time to do it. Uh, Let me start by asking people if they have questions, because if not, then I have a couple of things to ask. Anyone online? No? Let me start with one then. So just for background, I was one of the authors on the first and second IPCC reports. And your closing slide before this one, where you were pointing out the deficiency of the climate models and why we urgently need to do something, is what we wrote in 1996. So, and
Yes.
then I look at your paper, which is Global Emergence of Regional Heatwave Hotspots Outpaces Climate Model Simulations, and it makes me think that in reality, the climate of the future will be here before our models get to be able to describe it. And that's sort of, I think, the message you're trying to give very kindly on the thing. On the other hand, I would say that, during the 80s and 90s, I spent quite a bit of time with Ed Lorenz and Barry Saltzman. And that's a different world, because what you're doing is you're thinking about what are the implications of the physics in terms of what will happen. And one of the things you highlighted, which was that as the equator to pole temperature gradient weakens during warming, you end up with more persistent but disorganized sort of jet stream patterns, which then lead to more persistent high pressure centers and heat waves. So that prediction was there from the mouth of Ed Lorenz in 1990. So in some ways, I wonder, and most of the things you presented, which were very nicely done, so I'm not questioning them, but what I'm saying is these were features that we knew from the science background without being specific. And the diagnosis of wave numbers 3, 5, and 7 and their persistence or re-emergence in the same spots also has been known for about 30 years. What are we missing? Why are we not putting this together and giving the story to people in words that they can understand, instead of relying on models which we repeatedly show cannot reproduce historical data?
Yeah, uh, thanks a lot for the context. And yeah, if you could send me that one paper that you mentioned by Ed Lawrence, I'd be super excited to read it. I know that happens in science a lot, that certain concepts are discussed in papers, then they kind of disappear a bit from the discourse, and then they re-emerge because all of a sudden you see these things happening. And I think when I think back, my PhD, which I did, yeah, like 7 years ago, this was the time where these types of wave patterns just occurred almost every summer and actually led to impact. So it just, I guess back then we came from the other direction. We saw the impacts and we were wondering what is going on in terms of physics, while Ed Lawrence saw the physics, but was possibly not yet aware of potential impacts, or maybe that was not necessarily like in his focus area back then. Um, but I mean, I feel like this is uh, encouraging that we as scientists, we do to some degree understand what is going on. Um, I I I think it's important. I would like to also give credit to climate models. I think the way I framed it now seems that the climate models are just failing at everything, which is incredibly unfair. And they also have improved a lot over the past decades. For instance, that uh, weakening of the storm tracks, that is a signal that CMIP 5 models have not really been able to capture, but CMIP 6 models are able to capture it. So I think we are getting closer, but you're right, that is my sentiment as well, that we do understand things at a certain pace, or we're like putting pieces together, but the speed at which these changes occur kind of outpaces, to use that term again, our ability to make sense of them and also to react. And that alone, I think, is a very dire and strong argument for mitigating emissions, of course, right? So
Sure.
the tools that we need to make better estimates of future risks, they will take a while until we have them, even with AI and these bigger computing capacities that have been emerging, because yeah, the physical understanding also needs to come in, right? And that I think is not what AI can do alone.
Mhm.
Um, Yeah, I don't know if I answered your question, but I found your comment very, very interesting. And um, yeah, I guess
I mean,
it
I
is
think
it is more for
partially,
social
firstly,
scientists to explain why we're not reacting to these
yeah. I mean,
warnings that
partially my
we're
comment
issuing.
was in reaction to your comment, which I totally agree with, that people who are doing the downscaling of these things and then passing that on are possibly amplifying the risk because they may be misinforming people.
Yeah,
And that's where I think, since we know, as you pointed out, where these wave number patterns typically re-emerge, this is a current risk, it's not even a future risk, yet people are not responding to the current risk. So if we ask them to respond to a speculative risk in the future, it's harder. The point that we need to mitigate this direction is very clear. Most people get it. The adaptation point, people are lost. What exactly are we supposed to do when you can't give me precision, right? So I think
yeah.
that's what the spirit of it. But let me stop and see if any of the audience have a question for you. No? Okay. Well, I think
No
we could
problem.
have a very nice chat for a long time, but
I'd love
it's
to do
also
that.
late for you, and so I'll let you go. And I look forward to meeting you here in Arizona at some point.
That would be great. And yeah, thanks everyone for listening. Again, thanks for the invitation.